Hey guys, and welcome to today's video. This is going to be part 2 in my series called Essentials of Critical Power, which is going to be a 3-part series. Today's video is going to be talking about the data collection and mathematics of critical power. So, right off the bat, I want to get into some limitations about this whole concept of being able to predict performance and using critical power in training and exercise prescription. So first off, critical power and W prime have no standardization yet. In other words, there are guidelines and different test protocols and things like that, but there is no set idea that you must do it like this. It's kind of like, here's some guidelines, these are things you should be aware of, and the accuracy is going to be dependent on, one, the effort of the person that is being tested, and then also the mathematical model that you choose to use, or the amount of sessions that you choose to find the linear regression or the calculation for critical power and W prime with. So getting right into it, the first way, and really the gold standard so far, at least that I've read, of calculating critical power or testing for critical power is going to be using multiple constant work rate tests, and then finding the slope of the y and x values. So let's say that you had a time trial, or you had somebody on the treadmill and you said, I'm going to set it to 6 miles per hour, and I want you to go until you can't go anymore. 6 miles per hour might be a bad example. Maybe if you had the person run at 10 miles an hour, and then you said, go as long as you possibly can. Basically, the hope is that that person is going to exhaust within 2 to 15 minutes, and you're going to repeat tests of this nature, and then at the end, you're going to do some calculations to figure out critical power and W prime. And again, there are no guidelines. There's no protocol that's set, but these are the guidelines that you should follow. So once we get the values of basically, let's say they ran or swam or whatever, a distance that we wanted them to go, and then how fast they completed that distance, or we had them work at a certain workload, and then we saw how long it took them to fatigue. Whatever it is, you have an X and a Y value for each of your trials. And doing so, you can find the slope and the y-intercept of all of your trials. And so what you're going to see is that initially there's going to be a hyperbolic relationship between power and time, or not distance and time, but speed and time, same thing. However, the goal is to make this as simple as possible. So what we do is we just convert this hyperbolic relationship into a linear one using either distance and time, or by taking the slope and y-intercept of critical power and W prime and the inverse of time in the case of power, as you can see over here. So again, we're taking the values that are naturally a hyperbolic relationship, and then we're converting them into this simply by finding the slope and then the y-intercept, which give us critical power and W prime. And if this was in speed terms, this would be like a swimmer or a runner or something like that, not a cyclist. This would be critical speed, and this would be D prime. Okay, so another way to test for critical power or critical speed is going to be the 3-minute all-out test. Now this test on the surface level might look more appealing. It's one test, it takes 3 minutes. It can determine more values than a typical, that gold standard critical power testing can. However, from personal experience and experience of people that have also done this test, I can tell you that this is probably the hardest test that you'll ever do. Thus, the validity behind the value is very dependent on the effort that that person is willing to push themselves. If you're not willing to push yourself, or you're not proficient in the modality that is being tested, then this is probably not a good test, because you're really just going to get unreliable data that's not really going to tell you a whole lot, and it's just going to tire out your athlete or whoever you're training, and they're probably not going to like you very much. So that test is we'll see what the future holds for that. So if you did decide to do the 3-minute all-out test, it actually is very simple to determine critical power and W prime or D prime and critical speed. As you can see, critical speed in this case is just going to be the last 30 seconds, the average of the speed in the last 30 seconds. And then D prime is going to be this equation right here. This diagram from a very popular paper lays it out very nicely. So again, like I said, there are some bonus variables that we get from doing the 3-minute all-out test, which is maximal sprint speed. So which in the first 50 meters or the first 10 seconds, we're probably going to find the maximal sprint speed that that person's going to reach, because this is, again, an unpaced, all-out, hence the name, effort. The second thing you'll be able to get in addition to all these variables is going to be the speed at VO2 max, which is hypothetically going to be the speed that they're at 90 seconds within the test. So now that we've chosen either the repeated measures or the repeated bout or the 3-minute all out, it doesn't matter. Once we've calculated and found critical power, critical speed, whatever, now we can really map out what kind of basically domains of intensity this person can exercise at, right? We can basically now target workloads, external workloads with internal workloads, and thus create adaptation from it, specific adaptation. So we can see that everything above critical power or critical speed is going to be considered HIIT training intensity, and then everything below that is going to be what's called moderate intensity continuous training. You might see some of these terms intermixed, for example, like the maximal lactic steady state in VT2, and then critical power and critical speed and end test power, which is VP. However, some people argue that these are not the same thing, myself included, but for the simplicity of today's video, let's just say they're the same thing. You also see that we have maximum aerobic speed, which is coming from the 30-15 intermittent fitness test. And that's just going to be the speed at which can elicit VO2 max, the lowest speed at which can elicit VO2 max. And then the domain in between maximal sprint speed and this VO2 max speed is going to be the anaerobic speed reserve, which is just basically the workload that doesn't rely on aerobic metabolism, because VO2 max, again, is aerobic metabolism. It's the consumption of oxygen, and so up until you hit VO2 max, you are relying on oxygen consumption, no matter what intensity you are, except for when you go above it, which is going to be, there's going to be much different limiting factors like neuromuscular limitations, things like that. So once we figured all this out, that's fine and dandy, but the problem is that we've already done this with a cardiopulmonary exercise test, with a gas exchanged measurement. So what's so special about critical power if we could have just done all of this with one test on a treadmill or on a bike? So the cool part is that we can predict performance unlike we can with a cardiopulmonary exercise test. With critical power and W prime, or critical speed and D prime, we can rearrange that linear regression into a whole lot of predictions. So we can predict how long it's going to take somebody to complete a race, like a 5K, and it really just goes back to basic algebra, rearranging equation and finding the unknown from the known. So you can see there are many ways we can rearrange the equations, and there are many different questions that we can answer. Now keep in mind that these are all going to be maximal estimations. If the person did the test correctly, which should be to complete exhaustion, each trial or in the 3-minute all out, the prediction you get is going to be a complete exhaustion prediction. Thus, you don't want to make that your target in training. However, that's going to be in part 3 of this series, where I actually talk about more athlete-specific, like actual situational specific stuff. So the next thing that's really cool is that we can not only predict one race or one session of a continuous workload, but we can also predict intermittent exercise tolerance as well through what's called the W balance model. this model, in a nutshell, to me, is basically giving us a way to predict the human battery and how it recharges and depletes at intensities above critical power. So a great analogy that I wish I could take credit for but can't is looking at savings and income. So basically, if you have a savings of W prime, which is, again, going to be this fixed capacity above critical power, and then you have your income, which is critical power. If you wanted to do an aerobic spending, in other words, a spending that didn't spend your savings, you could only spend up to $5,000 a month, right? If you want to do anaerobic spending, or you want to spend more aggressively, then you could spend more than $5,000, but you need to use your savings to cover those costs. So essentially what you can do is, for a certain budget, if you say 60% of savings per month, then you can predict how many months is it going to take for you to run out of your savings. So in the end of the day, when you look at this equation, you can see that every month you're going to lose 1,000, and then eventually by 10 months, you won't have any savings anymore. And supposedly exercise can be estimated this way. So this is just the same exact thing, but just translated into exercise terms. So instead of dollars, we have kilojoules, and instead of budget, we have desired exertion. Let's say we want 60% of capacity drained from each rep, which I would consider a light exertion. How many reps can I keep that up for? Again, with the same exact numbers, we can predict that this person would last approximately 10 reps before they exhausted. Is it that easy? That seems like super easy to predict performance. Unfortunately, it's not. So basically, the whole point of everything we're talking about is to take an external load prescription, so like wattage or speed or whatever, and then try to estimate what's happening inside the body, right? Try to estimate how much work can this person do, because the limitation is always going to be inside the body. Some of these terms right here are used to create the equations. And then a lot of the assumptions are, of course, that above critical power, that's depletion. So the work you're doing has to be above it, because then essentially you could work forever, or it would be substrate utilization limited instead of W prime limited. And then your rest needs to be below critical power, because you don't reconstitute energy above critical power. So you would just keep depleting if you had a rest workload above critical power. The mean power of the session should also be greater than critical power, because then essentially you would just be gaining energy in a mathematical model, which wouldn't make any sense. And then also in this particular model, the gain and drain happens at the same rate. So what would that look like? Basically, the drain would be equal to the power of the work minus critical power times the time of the work, and then the gain would be critical power minus the power of the rest divided by the time of the rest. And so your net effect is going to be gain minus drain, right? And that would give us an idea of how long it's going to take for this person to fatigue. And this is going to tell you 100% how to do that. So let's superimpose what your reps would look like. So rep 1, this is the work, and then you deplete, but then you rest, right? And then it goes up. So this is actually a little off. I apologize. These should be wider. But basically, you can see that we predict that within 5 reps, this person is probably going to fatigue. So the unfortunate truth is that this is not that simple. And we can see over here that it's more curvilinear in restoration. So in my opinion, it's obvious because of EPOC. EPOC describes that the replenishment of ATP takes longer than it takes to use up the energy. We can see in this example as well. And then we can also see with this chart that ATP does not replenish linearly as time goes on. Unfortunately, I don't know a whole lot about this, so please learn it and then teach it to me. These are my references. Be on the lookout for application of CP coming soon. Thank you for watching.